Hi, I'm Michael David Johnson. I'm a PhD student over at the University of Sheffield, and I'm very much interested in directly recovering surface parameters. At the moment of this presentation, it's more about the amplitude and the wavelength and the phase, for instance, of a rough surface. This presentation will quickly go over the applications of using a random forest to recover these from phase-removed acoustic data, and hopefully I haven't put too much maths in. So why would we even want to use an acoustic situation in this problem? Well, it's relatively inexpensive, and we can deploy it fast. Ideally, we could do a drone-based approach or other things like that. And also, we know that it can link the surface to the flow, so it's beneficial if we can do it with acoustics. Then it's another useful tool, basically. And because we're using a machine learning approach, the actual inversion from the data, we don't necessarily require any extra information or assumptions from physics or other inversion methods. It's kind of it's all in the forward model. So the general approach to this is usually pretty simple. We effectively just want to create a really large and accurate database formed of solutions to the forward problem. So the forward problem I'll describe later on in this presentation. It's just a tangent plane approximation, and then we just choose a suitable machine learning model that will apply to this very well, and then we optimize it pretty much. So the forward problem, how do we get data? Well, it would be ideal if we had lots and lots of data in field, but especially when we're validating methods, it's not very beneficial. So we're going to use something called the Kerkov approximation formula or the tangent plane approximation formula. And effectively, we're just given surface parameters and other information about microphones and sources, and we can get information from the acoustic, get estimated data of the acoustic pressure, as long as the surface satisfies the Kerkov approximation formula, which just bounds the fact that the surface can't be too bumpy, because we're going to be avoiding multiple scattering situations. So a slide of maths, it's kind of forced in a way, but all this integral is saying is we have this surface, and on the top right, if you can see my mouse, and we're going to project it down to a line. So if it's in 3 dimensions, we'll project it down to a flat plane. We'll map the elevation function as just a function that dictates the distance from that line to the surface, and then from that we get to a point in the surface, and we just imagine we've drawn an infinite tangential plane from that point, and we just reflect in a general way from a tangent line. So in this case here, we have R1 and R2, which is going to be just our Euclidean distances from the source and receiver, and our function of elevation is going to be encoded in this gamma, which is going to be the derivative. No, but it shouldn't be the derivative. It should just be the surface function. Sorry. So we know, because we're going to place the sources and receivers in space, and we know the frequency, we know every other parameter when it comes to the inversion. We just don't know the surface elevation function, which is what we're going to try and estimate. And instead of estimating pointwise, so just having an array of points on the surface, we're going to try and just directly get parameters of the surface, and then we're going to infer behavior from the parameters of the surface. So in this case, again, it's going to be the amplitude, the wavelength, and the phase of the surface. Again, so we can create data, we can create high quality data. It's already been validated before, high quality data relatively quickly, and we can just make a big matrix of input data and output data that we can use later on. So we can have the P's in this situation here are going to be the pressures of the microphones. We're going to take the absolute value, we're going to remove the phase, and we'll modify it with some Gaussian noise, which will be scaled between values of the percentages of the mean of the whole row of pressures. And then the surface values here will be, for instance, for just us, it's a single sinusoidal surface, as we'll talk on later, just the amplitude wave and phase. So let's quickly talk about random forests. Effectively, we have to start off with a decision tree. It's just a simple object, a tree-like object, which has all the data at the top, and then we should have some leaves at the bottom, and those leaves will be effectively pure. So if you go all the way down to the bottom of the leaf, then we'll have every single thing, if it's classification, everything will be classified the same, or in regression, they'll be within epsilon distance of each other, the actual outputs. So a quick toy example of this also, which will show the key features of a tree. This little toy example of it is just going to classify some fruit. So in these values, we have like 2 apples, 2 oranges, 1 lemon, or something. And we basically ask informed questions on the data, and whichever is informed the most, we can split down the whole way, which then leads to these leaves, which are completely the same. Which is a disaster in a way, because it's going to naturally lead to other things. So we established this by incorporating something called a random forest. So instead of having one tree, we'll have hundreds of trees, and those individual trees will only have a random subset of the samples as well as the microphone values. So some of them will only have, like, say, 5 values of the receivers, but that'll all be random. And then we aggregate all these results and we take an average. And that average should reduce overfitting and increase performance. So now we can start talking. So we have data on a static surface, which was made in CAD, and then acoustically rigid and then tested. So we can test this first, and then we move on to a moving surface, which was made in a water lab over at Leuven. So we assume the randomness is in one direction, and we have the source and receivers above the surface in a similar situation to like this. So we have effectively this situation where we can have any sort of surface at the bottom, again, as long as it satisfies the properties. And with a linear array of microphones, we can situate this with, I think we use 34 microphones in our situation here. And we have an angled source. So what we can do is we can create data in a very uniform way. We know what the surface is going to be, and we can associate this with a family of surfaces instead as well. We just generate values of the amplitude, phase, and wavelength, and we can just generate a massive data set, which is going to then be used in our inverse problem. And then we add noise, and we, in the usual way, we'll split into training and testing set. And we'll validate that with coefficient of determination for testing on the synthetic data set, which is just a metric that will try and explain how well the model can test against the variance of the created set. And we'll use RMSE in comparison to actually recovering surface parameters from real-world experimental situations. So we've done this for both. So if I can lead your eyes to the right-hand side, this is going to be our coefficient determination for free parameter recovery. So all the parameters shown before. So we're trying to recover the amplitude, the wavelength, and the phase of the surface, and we're going to explain the variance as the noise level increases. 1 is the perfect value, and we can go artificially negative. But once you get to 0, it's pretty much pointless. It just explains its own. It'll just take the mean as the sample. So if we have a look on the right hand side, even with a random forest and a low number of receivers, if you have a low number of noise in a simple situation, then it can explain the synthetic data set with a high level of accuracy to itself, which is very good. And we can increase the noise level further and further and still have some quite high robustness. But the issue is obviously when we go to larger and larger amounts of noise, then we start seeing the decay get worse and worse. And on the left-hand side, we have the RMSE for each parameter. So we're going to compare the real surface, which was around 1.5 millimeters in amplitude, 0.05 meters in wavelength, and then it was centered at 0, so there's no phase. And in this case, if we have a look at the amplitude, we can clearly see that for the red line, which is the full set of receivers here, located in space, we have very bad RMSE until we reach 15% noise, and then it starts increasing again. Whereas we have opposite behavior on the other ones. We modeled the error from the Kerkov approximation forward model to what we obtained in lab with this experiment, and the error in RMSE was around 17 to 19% so in the same way that I was generating the noise earlier. So it seems to behave for the full set of receivers similar to what I'd expect. And when we look at the wavelength specifically, the full set of receivers just shows that it's the way to go. So even with 34 receivers, but going any lower than 34, we have much worse performance. And phase kind of just does its own thing, which is directly modified by the noise. The more noise you get in, the worse phase. So we can actually look at how this actually recovers the actual surface, and we can see trends throughout. We can see the decrease in amplitude as the phase increases, and there's a slight phase shift. This is at 15% noise. It's very valuable. So we can extend this to moving surface. Can this work on a moving surface? So this is data collected by Dr. Giulio Dolcetti in collaboration with Siemens, using the water tank. They generated a surface that's very similar to the static surface, only order of magnitude smaller in amplitude. And can we do it? Can we do the exact same thing, instantaneously recover a moving surface from this? Well, turns out it's not too straightforward. Because it's a similar problem. We have the exact same behavior in R2 score as we saw in the earlier figures, which is great. However, when applying it to the actual data we have terrible RMSE. The amplitude is not predicted at all. The wavelength is doubled and the phase is moving, but nowhere near related to the speed of the wave, which is bad. And this could be down to a disconnect between the Kerkov approximation and the data due to in-field errors, or it could be that there's an issue with instantaneously recovering the surface, which is probably the more realistic option. So at the moment, I'm working on towards changing the forward model to be a more time average solution. When we go to more time average solutions, then we can go straight to velocity from there directly. But at the moment, that's what I'm working on right now. However, it's pretty promising overall in terms of the robustness to noise. So quick conclusion, machine learning has worked to recover surface parameters, and we've recovered more complicated surface parameters than shown in this presentation as well. It can be done especially for static surfaces, which is robust to noise. However, dynamic surfaces and moving surfaces in open channel flow does need more work, specifically in acoustic recovery using Kirchhoff approximation. Thank you very much. I think I just made 12 minutes.
12 minutes 23. Well done. I'd like to open the floor up for questions. Does anyone have any questions for Michael David?
Hello, can you hear me?
Hi, yes.
Yes.
Yeah, this is Dr. Balan calling from India. The experiment setup, what you have shown, had some source and array of detectors. Can you tell me what was, yes. Can you tell me what was the frequency in which you operated and what was the receiver gains you used for this setup?
I can't remember the receiver gain specifically, but the source frequency I used was 14,000 hertz.
Okay, so it is in the kilohertz, 1.4 kilohertz?
Yes.
Okay, yeah, that's one. Okay, good. These are all hydrophones, I believe, right? These are all hydrophones.
I can't remember the specific setup of the experiment myself because I wasn't there personally. So I have a text document that explains it.
Okay. Okay. The other question is, have you done an experiment to see how much maximum the source can be, deformed or moved so that the receivers can pick up the signal equally well? Have you done that part?
Yeah. So I've moved the source and the receivers around before. Usually it's fine as long as at least one of them, usually the microphones, but usually both the source and the microphones are in the acoustic far field. As long as you move them far away, it's fine. If you move it far away and then have a high wavelength, then you get more errors, especially when you compare against what you would recover in real experiments. So I think for me, even in this specific setup, which wasn't too far away, after about 23,000 hertz, you had a massive disconnect between what we received from the experiment and what the Kirchhoff approximation would estimate by a huge amount. So much that calibration would not even help. Like it was terrible.